current project. Okay, there are 3 ingredients. First ingredient. Dynamics models are expensive, but if you want to run tens, hundreds, thousands, eventually you're going to hit some kind of limit, and you'd like to decouple that somehow from being a bottleneck. So I'm going to throw that in the cauldron. Ingredient number 2. I like MATLAB. MATLAB is great for visualization. MATLAB is great for rapid prototyping. It would be cool to offload as much as possible onto MATLAB. However, the software infrastructure for controlling the ActHand is not in MATLAB, and MATLAB can have problems with speed. Throw that in the cauldron. Third element is that muscle models are inherently stabilizing. The models of how muscles respond to neural activation look with details like a spring damper system. So there's a preferred place, and there's an attractor there, and as you sort of stimulate muscles, you get dynamically stable deviations from that attractor state. So we'll throw those all in the cauldron, see what comes out. Okay, this is what comes out. You want controllers that are decoupled from the system through a network, and that network will interface them with a really rapidly running and therefore stable for the robot controller, a behavior that goes really fast, like 200 hertz. The way that that behavior will deal with the asynchronicity, heterogeneity, and sort of remote slowness of the bank of controllers is by running a muscle model. So, from a robotics point of view, what you want is the simplest stabilizing muscle model. So that looks something like this. The torque that is output by a motor, a muscle, is a function of its length, its velocity, and its activation. Its activation is some kind of low-pass filter on the neural commands that it's receiving. The dependence on length and velocity looks something like this. This is length. There's an active component, and then as you extend the length, you get a passive component. In the velocity curve, you're able to really develop lots of forces when you are contracting, when you're lengthening, and then as you're contracting, you're less able to develop forces. And then when you combine those together, you get this wacky surface that's a function of all those things, and that should be inherently enough. However, if you're interested in taking the anthropomorphic angle instead of sort of the straight robot control angle, there are far more complete, like Brown and Loeb muscle models, and these guys have really conscientiously estimated sort of parameter values for various muscles, and they model a lot more of the weird properties of muscles. However, I think for the first pass, the way to go is with the simple guys instead of these more complex guys. That is my summary of what I'm doing right now.